Hello, everyone. Welcome to the ILTA Physics online problem-solving lecture. Today, we are going to study centripetal force in circular motion. The inward pulling force that makes an object's path circular is called centripetal force. When you see a uniform circular motion problem, you should always keep the following diagram in mind. An object tries to move forward with a constant speed, but since acceleration acts perpendicular to this velocity, the object follows a circular path. The force that creates this centripetal acceleration is the centripetal force. Therefore, you can think of centripetal force as the inward pull that keeps an object moving in a circular orbit. The basic type of centripetal force problem involves finding centripetal acceleration and centripetal force using the basic formulas for circular motion. However, since centripetal force is still a force, some problems will require a motion analysis using a free body diagram to account for the various forces acting on the object. Now, let's briefly summarize the basic formulas of circular motion and centripetal force. Motion where an object moves at a constant speed along a circular path is called uniform circular motion. As shown in the figure on the right, the object maintains a circular orbit because there is an inward acceleration acting at 90 degrees to the direction of motion. This centripetal acceleration is produced by the centripetal force. An important characteristic of this circular motion is that the object's velocity is always tangential to the circular path and is always perpendicular to the centripetal acceleration. The main formulas related to circular motion are as follows. Centripetal acceleration is proportional to the square of the velocity and inversely proportional to the radius. According to Newton's second law, centripetal force is calculated as the product of mass and centripetal acceleration. Also, since circular motion is a classic example of periodic motion, there are many types of problems using period or frequency. The velocity of an object in circular motion can also be calculated by dividing the distance traveled by the time interval, based on the definition of velocity. Therefore, in the case of circular motion, you can find the velocity by dividing the circumference of one full rotation by the period, which is the time it takes to complete one lap. Since frequency is the reciprocal of the period, this can also be expressed as a function of frequency. Furthermore, based on the relationship between velocity and centripetal acceleration mentioned earlier, we can express centripetal acceleration as a function of period and frequency as follows. You don't need to memorize every single one of these formulas. If you accurately understand the most basic formula for centripetal acceleration, you can easily derive all the other relationships using Newton's law of acceleration or the definition of velocity. Since centripetal force is a type of force, a free body diagram is necessary to visually represent all the forces acting on an object when calculating dynamics. A free body diagram is a very common method used to consider the net force acting on an object. If an object is moving on an inclined plane, we sometimes analyze it by breaking the forces into parallel and perpendicular components. Now let's solve some basic problems regarding centripetal force in circular motion. Problem number 16 is about finding the static friction force using centripetal force in the motion of a cyclist performing circular motion. It's a type where several concepts are intertwined, but you can just follow along step by step. Looking at the figure on the right, a cyclist riding through a curve experiences a centripetal force toward the center of the circle, which is the inward direction. However, the reason the cyclist doesn't suddenly slide inward is that a frictional force of the same magnitude is acting in the opposite direction of the centripetal force. One question might come to mind here. Since the bicycle is moving, why are we asking for static friction instead of kinetic friction? Usually, it's easy to think of kinetic friction for a moving object, but we only use kinetic friction when considering the friction in the direction the bicycle is traveling along the curved path. However, this problem is asking for the friction that balances the centripetal force at that exact moment of turning the corner, so it is correct to apply static friction. Now let's draw a free body diagram for this cyclist to organize the force relationships. Assuming the direction the bicycle is moving is forward, the four forces acting on the object at that moment are as follows. Most basically, the weight or gravity pulled by the Earth acts downward, and a normal force of the same magnitude acts upward. And since it is in circular motion, centripetal force acts to the right, while static friction of the same magnitude acts in the opposite direction to the left. First, according to Newton's second law, centripetal force can be expressed as mass times centripetal acceleration. Here, centripetal acceleration is expressed in terms of velocity and radius. Meanwhile, static friction is calculated as normal force times the coefficient of static friction. Since the normal force is equal in magnitude to the weight, it can be organized into the following equation. The reason the bicycle can turn the corner well without falling inward or sliding outward is that the centripetal force and static friction are in equilibrium. By combining these two equations to solve for the coefficient of static friction, it becomes the value of centripetal acceleration divided by the acceleration due to gravity. Substituting the values given in the problem, the coefficient of static friction comes out to 0.735. Please also remember that the coefficient of friction has no units because it is a ratio of two forces. For problem number 20, let's calculate the centripetal force acting on the blade of a wind turbine in circular motion. As shown in the figure on the right, the total length of the blade is 38 meters, and the problem asks for the centripetal acceleration at the center of mass, assuming it is exactly at the midpoint. In this problem, the rotational speed of the wind turbine blade is given as an RPM value. RPM is a type of frequency, but we need to convert it into a frequency value that shows how many times it rotates in 1 second to make it easier to use in our formulas. Dividing the RPM by 60 seconds, the frequency of the wind turbine comes out to 0.37. If we know the frequency, we can find the centripetal acceleration according to the formulas we learned. Of course, it's fine if you have the formula below memorized, or you can simply derive it from the circular motion relationships we understood earlier. The thing to be careful about here is the value of the radius, r. Since the entire blade is 38 meters and the center of mass is in the middle, we must use half of that, which is 19 meters, for the radius. This corresponds to the position of the red dot in the figure. Calculating this way, the centripetal acceleration comes out to 100.4 meters per second squared. Finally, the centripetal force acting on the blade can be found by multiplying this centripetal acceleration by the mass. The calculated result is 1.2 times 10 to the 6th power newtons. Since the weight of a single wind turbine blade is so large, we can confirm through calculation that the centripetal force the blade must withstand while rotating is truly enormous, even if it isn't rotating at a very high speed. That's it for today's lecture. Great job, everyone. I'll see you in the next session.